this video, we're going to look at how to perform a hypothesis test for quantitative variables using R. So as usual, there's a couple files that you'll want to have handy. The first one is the R script for this module. You'll also want to have the Kentucky 2020 data set if you're going to follow along with me, or the data set for your state. You'll also want to make sure that you have the code book handy, as well as the corresponding note set. Alright, so the first thing we're going to do is read in the Kentucky data set. So this is the same as we've done in previous modules. I'm going to use the head function just to kind of scroll through and make sure everything looks like it should, and it does. And I have the number of observations and the number of variables that I expect. Alright, so the first hypothesis we're going to look at is the one sample t-test. So we'll start out here in the notes. So recall that a one sample t-test can help answer questions like, at the 5% significance level, is the mean BMI of people living in Kentucky during the year 2020 greater than 25? So notice here we're going to see if the average BMI for people living in Kentucky is greater than 25. Here 25 is chosen because a BMI over 25 is outside of the healthy range towards overweight and obese. And so we're going to use the 2020 data to help us answer this question. Alright, so first to run the code, we're going to need to explore that BMI variable. So let's first look at the BMI variable in the code book. Alright, so here is our variable. Notice this is one of the variables that starts with an underscore, so to call it an R, I'm going to have to put an X in front of it. Also notice that we have two implied decimal places. So in other words, if we have a BMI of 2500, that's really a BMI of 25. Alright, so the first thing I'm going to do is assign the BMI variable to be equal to BMI var. And you'll notice here I've divided by 100. And so what that does is that takes care of those two implied decimal places. I don't have to do this, but if I don't do this, then I'll have to remember that everything is going to have the two implied decimal places. So instead of comparing to 25, I would need to compare to 2500. Alright, so I'm going to read that in. Next, we always want to look at a histogram. So notice here we have a very, very slight right skew to the BMI variable, but it is fairly normal. We're going to see if there are any missing values. And what we're going to do is check the total sample size here. So remember that the is.na, that's going to count the number of missing values. Putting the exclamation in front of it counts how many are not missing. And so this tells us that there are 2,669 observations that are going to go into the calculation. That is more than large enough for the central limit theorem, where we only need a sample size of 30, so we're going to meet our assumptions. And then it's always a good idea just to look at the mean of the sample as well. And so we see the mean of the sample is 29.27, which is obviously higher than 25. And so now our question is going to be, since that's what's occurring in the sample, is that enough evidence to suggest that is also happening in the population? So here is our code to perform the test. We're going to call the t.test function. We're going to give it our BMI variable. Mu equal to 25 is the value under the null hypothesis. And here we're testing to see if that mean is greater than 25, so our alternative is going to be greater. And remember, anytime we have missing values, we also need to include this na.rm equals true. So we will run this. And here are our results. I have pasted those results here in the notes. So a couple things to notice here. One, it's going to give us the mean of our sample, so there's that 29.27. We also get a confidence interval, which we've seen previously. And then highlighted here in teal are the results of the hypothesis test. And so notice here that we do have a very small p-value here. So anytime you see this scientific notation, this essentially means there are 15 leading zeros, so 15 zeros and then 2, 2. right? So we definitely are significant in this case. So just a couple data notes. We note that from the code book there were those 2 implied decimal places. We had a random sample and a sample size of at least 30, so we met the assumptions. So now we can make our conclusion. At the 5% significance level, we have evidence that the mean BMI of people living in Kentucky during the year 2020 is greater than 25. And so one thing to notice here is in that use of the language of significant. I'm never going to say something is very significant or extremely significant. It's either significant or it's not significant. All right, let's look at our next hypothesis test. Next, we're going to look at a 2-sample t-test using independent samples. Now, you may notice here that I'm skipping over the paired t-test that you saw earlier in the note set. The reason for this is using the BRFSS data, we don't have any paired data, so we can't do that one for the BRFSS. So we are going to move straight to the 2-sample t-test. So the 2-sample t-test that we're going to be looking at here is, and I'm just making a slight correction here, this will be corrected on your version, is at the 5% significance level, is the mean BMI for people living in Kentucky with good, better health different than the mean BMI in people living in Kentucky with fair, poor health during the year 2020? So again, we can use R to help us perform this hypothesis test. So the first thing I'm going to do is create the variables that I need. I already created BMI up above, but just in case we hadn't performed that first one first, you need to create the BMI variable, and then we're also going to create the health variable. So again, let's look at this variable in the code book. All right, so here is our variable, and we can see that it takes the values 1, 2, and 9, and we've seen this variable in the past. So what I'm going to do is I'm going to create 2 objects, good BMI and poor BMI. Good BMI is going to store the BMI values for those that have the health variable equal to 1, in other words, that good, better health. And poor BMI is going to store the BMI values for those that have the health var equal to 2, which is that fair, poor health. Right, so we create these. Right. Next, we're going to look at a histogram, and we're going to see the sample size for those that were in good health, their BMI. So we have 2,035 observations for that group. Also, we see again that slight right skew, but it is fairly normal. And our sample size is large enough that that won't matter. And then we'll do the same thing for the poor health. Now notice our sample size is a little bit smaller here. It's 627. It's perfectly fine that these 2 sample sizes are different for this t-test. Next, again, we're going to look at the mean and the standard deviation of each of the samples. Notice here that we can see that the mean for BMI for those in good health is lower than the mean BMI for those for poor health. We should note, though, that both of these are over that 25. Now, when performing a hypothesis test for difference in means, we need to decide if the population variances are equal or not. So a general rule to evaluate this is to use the sample standard deviations, and if the largest sample, and this should say standard deviation, divided by the smallest is greater than 2, then we would use the unequal variance test. So what we're going to do here is notice, if we look before, we see that for the poor BMI, they have a larger standard deviation than the good one. So what I'm going to do is divide the standard deviation for the poor health BMI divided by the standard deviation for the good health BMI. We see that's equal to 1.24. That is not over 2. So in this case, it would be reasonable to assume equal standard deviations. So we're going to run that t-test. So notice here we're using the same function as before. The only difference is I call the t.test. I'm going to have my good BMI, poor BMI. I'm going to set variance equal to true, and then na.rm equal to true. Now notice here I have not included the alternative that I did up here, and that's because by default it's going to do the not equal or the two-tail test. but I could add that in if I'm trying to test to see if one is greater than the other one or less than or equal to the other one. Now, if we did not want to assume that our variances were equal, we could have set the var.equal to false. All right, so running this, we already ran this, it was down here. So I'm going to copy this into our notes. Here we go. And you'll see here is that output copied. So a couple things to notice here. Here's where we had the mean BMI for those in good health, the mean BMI there for those in poor health. We have our confidence interval that we saw previously, and highlighted in teal is the results of the hypothesis test. So again, notice our p-value is very small. This is scientific notation, so there are 10 leading zeros and then 864. Here in our data note, we're going to note that we did have those 2 implied decimal places for BMI, and we're going to assume equal standard deviations for the analysis. We have random samples, and both groups have sample size of at least 30, so the central limit theorem applies. And now for our conclusion. At the 5% significance level, we have evidence that the mean BMI for people living in Kentucky with good better health is different than the mean BMI for people living in Kentucky with fair poor health during the year 2020. We can also add here that the sample suggests on average those with good health have a lower BMI compared to those with poor health. And that's because in the sample we do see that average BMI for those with the good better health is lower than the average BMI for those with the poor health. All right, our last hypothesis test that we are going to look at, or probably not second to last, not the very last one, is the Anova test. So an Anova test can answer a question like, at the 5% significance level, does the mean BMI for people living in Kentucky differ with respect to smokeless tobacco use? So again, let's go to our code. We're going to first look at this variable in the code book. Okay, so here's the variable. We can see that the options are every day, some days, not at all, don't know, not sure, and refused. So of course we're going to focus on the values 1, 2, and 3. So just like we did earlier with the health variable, what I'm going to do is we are going to find the BMI values for those that smoke every day, those that smoke some, and those that do not smoke. So again, just as a reminder, that's what those values represent. Right, so we're going to create this. So this is very similar to what we did in the previous step. I need to run that first line first. Okay. And now, just like before, we're going to look at a histogram and the number of observations in each of those groups. So here is for the everyday smokers, and we have 114 observations. Here are the someday smokers. We have 44 observations. And here is for the non-smokers, and we've got 2,469. Now it is okay that we have unequal sample sizes here. Next, we're going to look at the side-by-side box plots. Here it looks like our variability is reasonably the same. We do have some outliers here with the non-smoking group, but overall these look fairly similar. Also, if we went back through, all of our histograms are reasonably normal. We have slight right skews, but it's not too bad. Right. And then next, we can perform the hypothesis test. Now to do this, we have to create a new small data set. So what I'm going to do is create a data set called BMI data. I do this using the data frame function. First thing I have to do here is I have to create first a column that's going to contain all of my data. So this is going to contain the every BMI, the some BMI, and then no BMI. And then I have to create levels that represent the different smoking statuses. And so you'll notice here in this code, I've got the every, some, and not. And then I'm going to repeat that, the number of observations that are in every BMI, some BMI, and then the no BMI. Just looking at the first 10 rows of that new data set, this is what that looks like. So notice I've got the BMI and then I've got their smoking status. Then we can perform the Anova test using the AOV function and calling in that new data set that I just made. And then here's what that looks like. All right, so next in the notes, here we go. You'll see I have copied over that output. In this case, our hypothesis test was not significant. Now here's where we checked our assumptions. And then our conclusion here is at the 5% significance level, we do not have enough evidence that the mean BMI for people living in Kentucky differ with respect to smokeless tobacco use during the year 2020. Right, we have our last hypothesis test now. This one is how to perform a hypothesis test for linear regression. Here we could answer questions like, does the simple linear regression model with height as a predictor do a good job of explaining the variability? Oops, this should say of weight. Further, is there evidence that the slope of the line is non-zero? So again, we're going to use that 2020 BRFSS data, and we're going to perform our hypothesis test. Now I should note here with the Anova, there is a line of code here to do the multiple comparisons that you saw in the note set from 14.1. You only perform these multiple comparisons if the Anova was significant. Ours was not, and that's why I skipped over it. All right, so first, for the regression, we would create the scatter plot. You've seen this before, so I'm just going to go ahead and create this. So here is our scatter plot. We might want to look at the correlation between height and weight. So we see the correlation is 0.45. And you'll notice, just as a reminder, I've put the question mark in front of the correlation function. So if you want to read about that one, and you can see the different types of correlation it can compute. Next, we're going to fit the simple linear regression model. And you've actually seen this before when we added the regression line to the scatter plot. We just didn't really look at the output. So now I'm going to look at that output here in the note set. So here is that output. Here you have the hypothesis test where we're looking at whether or not the slope is 0. And here we have the overall f-test. So these actually contain the same information for simple linear regression. Notice again we have a significant result here. So we can say at the 5% significance level we have enough evidence to conclude that the simple linear regression model with height is a predictor, is doing a good job of explaining the variability, and again that should be weight. Further, there is evidence that the slope of the line is non-zero and there is a linear relationship between height and weight. So this is going to conclude this set of notes. So as always, if you have any questions about the code, you need any help, please let me know.